Welcome to another podcast. In this episode, we're going to be taking a look at how to correctly evaluate limits that involve absolute values. Now, as we get started here, I want to remind you of the definition of the absolute value. So let's start there. The absolute value of x is actually defined as a piecewise function of the form you get x if x is greater than or equal to 0, and you get negative x when x is less than 0. Now, most students, what they will remember from this is the graph of the function itself. It has sort of a special format. And so if we look at trying to graph this guy, then we're going to be looking at something like this. And so a graph of this, remember, it has sort of that special format. So I'll graph it here in a different color. We've got the left-hand side, which comes in, and then the right-hand side, which leaves. Something like, let's say that. This side is the side y equal x, because on this side, x is greater than or equal to 0. And on this side, this is y equal negative x, because on this side, x is less than 0, and it's defined to be 0 at 0. So this is the absolute value function. Clearly, if we were to start thinking about limits for this function based on the graph, we could say, fairly precisely here that the limit as x goes to 0 of the absolute value of x is equal to 0. Now, if we need to know why that is, then we have to sort of go back to an understanding of one-sided limits. To actually show that this limit is 0, I have to look at the limit as x approaches 0 from the right, and I have to look at the limit as x approaches 0 from the left. Now, if we're approaching 0 from the right, then we're on the curve y equals x, because that's to the right of 0. And so the absolute value of x becomes, if we're on the right-hand side, we're not looking at the absolute value, we're just looking at x on the right-hand side. And so plugging in x equal to 0, we get 0. On the left-hand side, so if we're approaching 0 from the left, then the function actually changes. It's actually defined to be negative x to the left of 0, so I'm using negative x to represent the function there. And so the limit there is also 0. Since the limit from the left and the limit from the right agree, that's why we can say quite confidently that the limit as x approaches 0 is 0, and you can clearly see that, as we approach from this direction and this direction, the y values are both heading towards 0. Now, that's not always going to be the case when absolute values are involved in a limit. Sometimes the limit will not exist. So I want to show you a couple of examples of this just to make sure that you're understanding how to properly evaluate limits that involve absolute values. So we're going to start with a fairly simple yet quite important limit here, and that is the limit as x goes to 0 of the absolute value of x divided by x. And when I look at this, I think of the absolute value of x over x as being kind of like 1, because if you just had x over x, it would be 1. The problem lies in the fact that the absolute value of x is actually negative x to the left of 0. And so if I wanted to evaluate this limit, I have to look at the limit from the left and the right. So let's do that. We'll start with the right. The limit from the right will replace the absolute value with just x, which makes this limit 1. And remember, the limit of a constant is the constant because there's no x in here that's changing. And so the limit from the right is 1. The limit from the left would get replaced with negative x instead, because approaching from the left, we have negative x. And so the limit I would be evaluating here is negative 1. And so what this says is that the limit from the left and the limit from the right don't agree. So this limit up here, this limit as x goes to 0 of the absolute value of x over x, we can say that this limit doesn't exist because the one-sided limits don't agree. And in fact, if I was to actually graph a picture of this, or graph a picture of the function here, it's simply just going to be -1 as we approach from the left, and it's going to have a value of 1 as we approach from the right. And so this is the function f of x equal the absolute value of x over x, and you can clearly see that we call this a jump. There's a jump at x equal to 0. So the limit from the left and the limit from the right don't agree. The reason that, by the way, that this is a closed-in circle is because if you go back to the definition of the absolute value, the right-hand side is the one that contains the value at 0. So it would be coming in from the right. This is where it would be defined at 0. So if you were to ask me what is f of 0, even though I can't officially evaluate it there, the way that the absolute value function is defined, f at 0 would be 1 for this particular function. All right, well, that's all well and good. A lot of times we'll be dealing with absolute values that aren't centered at 0 like this, and so we need to look at their limits at other points. So let's look at another example where that's the case. So if we have the limit as x goes to -3, let's say -2x minus 6 over -x minus 3, immediately we can see that, just like in the previous problem, plugging in x equal to 0 right away isn't going to work up here, just like plugging in -3 down here doesn't work, because if I plug in -3, I get a 0 on the bottom. So this fails the direct substitution property. I can't directly substitute in my limit. So I'm going to have to approach it, because of the absolute value, I'm going to approach it from both the left and the right. So I'm going to look at the limit as x approaches -3 from the right first. And from the right, -2x minus 6 doesn't change, but this absolute value, since we're approaching it from the right, I get whatever's inside the absolute value. So I don't change it. So what's in bottom is just this. Okay, well that's, if I do a little bit of algebra here, I'm going to pull out the negative from the top term. Actually, let me go ahead and pull out more than just the negative. They also share a common factor of 2. So let me pull out a -2 from that top term. Then we're going to get x plus 3. And then for the bottom term, if I pull out a negative from it as well, notice this x plus 3 factor appears in both. We're going to go ahead and cancel that here. And then what we notice is what's left is -2 on top and -1 on bottom, but that's just +2. And so if we evaluate this limit now, there is no x term left. They've all canceled out, and so we just have 2 as the limit there from the right. Well, if you approach this particular limit from the left, then there's no absolute value in the top, so approaching from the left and the right for the top term doesn't matter. But for the bottom term, the absolute value function would give the negative of whatever's inside. So if I negate what's inside the absolute value, then -x becomes +x, and -3 becomes +3. And so approaching from the left, this is what the function would look like. So here we have the limit as x goes to -3 from the left of, same deal, I'm going to pull out -2 here, and I get x plus 3 in the top. And I still have x plus 3 in the bottom. Well, the major difference now you can see is that the top has the negative, but there is no negative in the bottom anymore, because we negated it coming in from the left. So what you have left over here is -2, and the limit of that constant is itself, and so you get -2. These two don't agree. That's bad. Since there's no agreement here, then this original limit doesn't exist. The limits from the left and the limits from the right are not the same. In fact, the graph of this function, so if I was to graph this function here, its graph would be identical to this one, except there would be a couple of small changes. Let me show you what those changes are. Let me clear out a spot to draw in this graph here. That's too much. Bring that back. All right, let me draw in this graph real quick. the main difference in the graph will be where things are centered. So the breakover point here is occurring at -3. So you would have to the left of -3, you have -2. And to the right of -3, you have +2. So this is what the graph of this function f of x equal -2x minus 6 over the absolute value of -x minus 3. This is what this function would look like if you tried to graph it in your calculator. It's a weird function, but trying to actually calculate the limit in absolute value terms is kind of difficult if you can't look at the graph, right? Just looking at this function, you wouldn't necessarily know that the limit doesn't exist. In fact, you might not even know where to begin. But that was the purpose of this video, is to show you that if absolute values are involved, you have two different limits. You have a limit looking at x going to 0 from the right, and you also have a limit looking at x going to 0 from the left, or in this case, you can see clearly here that this is centered at x equal to 3, or excuse me, centered at x equal to -3. So I'm looking at the limit at -3 here rather than the limit at 0 for the actual function. All right, thank you for watching.